Now let's turn our attention to teaching model number 2. And indeed, using a wedge and dash is a great way to represent a particular enantiomer. So at the very top row, we see that we have a pair of chiral molecules that are enantiomers. They are mirror images that are not superposable, and we can call this a perspective formula type drawing. It can get actually a little bit tricky to show the three-dimensionality about chiral centers, especially if you have more than one chiral center. Now, Emil Fischer, a very famous chemist from the end of the 1800s who did a lot of work on stereochemistry as well as carbohydrate chemistry, realized that he needed a more efficient way to represent the stereochemistry of molecules. So he invented an approach which is called a Fischer projection, which allows us in a sense to take a shortcut to represent the three-dimensionality about chiral centers. So the idea is that you take that perspective drawing, which right now we're kind of seeing from the side view, and we turn those molecules such that the atoms that are on the horizontal are coming out at us. Or another way of thinking about it perhaps is if we stick our eyeball right here and look at the molecule, we would be seeing this. And in a similar way, if we stick our eyeball right here and look at the molecule, we would be seeing this. Or if it helps, we've just turned the molecules by 90 degrees. And again, the bromo and the hydrogen and the bromo are now on the horizontal. Okay, so that's important. Further, those atoms that are on the horizontal have to be coming out at us, whereas those atoms that are on the vertical must be going back. And then what Fischer did is he just used straight lines, but he understood that those things that are on the horizontal are in fact coming out at us. Okay, so he doesn't write that, but he understands that those things on the horizontal are coming out at us and those things on the vertical are going back. So that's the Fischer projection. When we get to carbohydrate chemistry later on, you'll see that this will be really important to be able to master. But actually, it's pretty important right now. One of the things that you may clearly see at this point is it's actually very apparent that these molecules are indeed mirror images, and certainly they would not be superposable. So I'd like you to develop the skill in being able to go back and forth between a perspective formula drawing as well as a Fischer projection. So let's give this a try. If you would turn your attention to the key question number 2, you're asked to draw the Fischer projection for two molecules A and B. Let's start with molecule A. Now, one of the things that might frustrate students a little bit is what they end up drawing could look different than what their neighbor ends up drawing, although the molecules could be the same. It all depends on the perspective that you take. To give you an idea of this, I'm going to take two different perspectives in drawing the Fischer projection for this particular molecule. Now at this stage, we really can't draw a Fischer projection unless we know the perspective drawing. So I'm going to arbitrarily say that the OH group is coming out at us, and therefore there's a hydrogen going back. And then I'm going to put my eyeball up here. That's a pretty funny looking eyeball, and I'm going to look down on that molecule. The other thing that I need to do is designate, when I'm looking down like this, what's going to be on top and what's going to be on bottom in my final diagram. So let us say we say the aldehyde group is going to be on top and the CH2OH group will be on the bottom. Hopefully you can project your point of view, your mind's eye, from where my eyeball is and you're looking down. And if on top is the aldehyde, there it would be. And if I'm looking down in the OH group, from our perspective right here is coming out at us, from the eyeball's perspective, the OH will be on the right-hand side, and the hydrogen will be on the left-hand side. Now, if you're having trouble visualizing this, you might want to get a set of toothpicks and some plasticine or marshmallows. Unfortunately, I'm not able to provide you with model kits, but something that allows you to see these things in 3 dimensions. At the bottom here, we'd have our CH2 and OH. Now, it really doesn't matter how I orient that bottom OH as long as I've got, this carbon down here. So again, it's the idea that these groups are coming out at us and these groups are going back. And that's what you would see if you were looking from my eyeball. Now I'm going to get rid of those wedge and dashes because I want to do a more legitimate Fischer projection. So that's what that would look like from the first perspective. Then we're going to draw the corresponding enantiomer. And actually then it's really easy to draw the enantiomer. And that is, I just draw this cross here. I put the aldehyde on the top. And then I put this OH here and the hydrogen here. And again, the OH. You can see I've drawn the mirror image. These would be non-superposable. Clearly, what we have in the middle here is a chiral center because 4 different groups are attached to it. So that would be from one perspective. Let's look from a different perspective to show how the Fischer projection can be drawn, and it'll arrive at the exact same set of structures, the pair of enantiomers. So let's say I put my eyeball down here and I'm looking this way. And as I'm looking in that fashion, then I would say actually these bonds here are coming out at me as I'm looking from my perspective with the eyeball here. So what that would look like is I would have my aldehyde group right here. It's coming out at me. And I'd have my CH2OH group coming out at me. And what's going back would be the OH group at the top here. And what's going back would be the hydrogen right here. Now again, I want to draw a proper Fischer projection, so I'm going to erase the dashes and just simply draw the cross here. The OH will be up there and the hydrogen will be down there. And then in turn, I can draw the mirror image. So draw my cross, the OH, C double bond O, CH2OH on that side, and the hydrogen down here. I'm going to label this as 1, and I'm going to label this as 2. So structures 1 and 2 are in fact identical. And one of the ways that you can confirm this is, you may remember from first year chemistry, if you switch any 2 groups, you end up with the enantiomer. So let's see what would be involved in trying to convert our structure 1 to structure number 2. And one of the things I notice is that I would need to interconvert the aldehyde right here and the OH group, like switch those 2 positions, right? So I'll switch those 2 positions and I end up with this and this. But that's not the only thing that happened. What happened also is that this and this got switched, and then I end up with this and this. So in order to interconvert between 1 and 2, you need to do 2 sets of switches. And if you're doing 2 sets of switches, of course, you end up with the identical molecule. So that's our first attempt at drawing Fischer projections and the corresponding enantiomers. So now I'd like you to apply this approach to molecule B and ask you to come up with the Fischer projection plus the corresponding enantiomer. Now in order to do this, I have to designate where the wedge and dash will be. So let's do this. We'll put the hydrogen going back. Now you'll notice this is the chiral carbon. And you'll also notice that you have a protonated amine plus a carboxylic acid and a CH3 group. Now, as it turns out, this is the amino acid aniline. And of course, this reinforces the idea that almost all of the naturally occurring amino acids are chiral, which in turn means that polymers of amino acids would be chiral. So therefore, our enzymes and other proteins that are physiologically important are chiral. And so certainly this whole idea of chirality and stereoisomers is infinitely important in the biological world. The one amino acid that's not chiral is glycine, where instead of having a CH3 group right here, there's just a hydrogen. So please pause the video and draw a Fischer projection. Okay, now again, it depends on where you put your eyeball. I'm going to put my eyeball up here and look down, and I'm going to say this is the top of my molecule with the carboxylic acid. So if that's the top of my molecule, I have the C double bond O, OH. I've got my cross at the bottom. I have a CH3 group, And if I'm looking down from my eyeball then, with this carboxylic acid on the top, well then I'll have the protonated amine over here and the hydrogen over there. In terms of the enantiomer, well then we've got the NH3 plus and the H and the carboxylic acid. Now perhaps one of the things that you might notice is it's actually quite efficient to draw a Fischer projection, and we're still giving the same information. And just for completeness, in case you did it a different way, let's say we put our eyeball down here and look upwards. So the Fischer projection in that case would be that you've got your carboxylic acid over here coming out at you. You've got your CH3 on the other side. And at the top you would have your protonated amine, and at the bottom you would have your hydrogen. And again, I can very quickly draw the enantiomer on this side with the protonated amine at the top, hydrogen, and the CH3 on the right. Again, we'll do more practice related to drawing Fischer projections, but it's well worth taking some time to master this approach.